Okay, good. So we need initialization, right? Initialization process to generate initial feasible solutions. Okay, it depends on the algorithm. Some algorithm requires multiple starting points. Okay, but some needs just only one point, one single point. Okay, and then the next one, we need iterative process. It involves two things. First, evaluate the objective function and also adjust the decision variable in a way that seek to gain better solution. Okay. So previously, last week, I told you about this process. Some algorithm require just only information of objective function, the value of the objective function itself, not the gradient. But some require gradient or other information. So right, depends on the algorithm. But most of them, you need two things. The first one is direction, right? From the initial point, you need the direction. Which direction? When we say direction, it means vector. Okay? In which direction we will follow? And how large the step size is. Okay? So you need two things, the direction and step size. Okay? And the last one, termination process. How we, repeat the iterative process. Okay? And of course, you cannot run forever, right? You need a termination criteria. Okay? It can be KKT conditions or other conditions. Okay? Because KKT condition is condition specifying the optimum point, right? But it doesn't consider the, computational efficiency or other things, right? Okay. And we skip out this, right? And last week, we discussed about the method, the algorithm to find the step size, right? Assume that you have direction or direction as given already, okay? And now we want to find how far we should go, okay? Or its step size, all right? Assume that we have direction already, okay? With direction, you map your original objective function to the new objective function. It's just estimated objective function in a specified direction, okay? Because in our original problem, we may have multiple decision variables, okay? But once you specify the direction, you map the original objective function to, an approximated or estimated objective function as a function of step size only, okay? So you map n-dimensional problem to a single variable problem, okay? Okay, so in order to find we need algorithm, right? In order to find the step size. And the algorithm to find the step size, we can broadly distinguish into two types. The first one is elimination method. And the second one is interpolation method, okay? For elimination method, of course, it's very simple. We start from, actually, we don't need a gradient. We don't need derivative, anything. We use the property of unimodal. If we assume that in a certain region, it is unimodal. And you know the property of unimodal, right? Because there's only one local optimum in the region we specify, okay? So by using elimination method, of course, we don't know exactly the shape of the function, but we can evaluate some points in the region of interest. Okay. Assume that our region of interest is starting from 0 to 1. Okay. And we can evaluate 2 points, x1 and x2. Okay. And if the result, the outcome, if we get this outcome, we know our local optimum cannot lie in this region, right? From x2 to 1. Okay. So we can eliminate this area out. Okay, from x2 to 1, right? In the figure A. Okay. So that is the reason why we call it elimination method, because we can eliminate some part, some area. Okay. And in figure B, we can be sure that our local optimum cannot lie in this region from 0 to x1, right? We can eliminate this part. Okay, on the leftmost. Okay. And for figure C, okay, we can eliminate two areas from 0 to x1 and x1 to x2 to 1. Okay. So we have several algorithms. The first one is an heuristic search, kind of search with a fixed step size. Okay. And we also have, I show you in the example. Also, we can adjust, modify the algorithm. This one is search with accelerated step size. Okay. And also we have exhaustive search. Okay. It depends on the number of points we evaluate. Okay. If we evaluate more points, of course, you can eliminate larger area. Okay. But you have to trade off with computational efficiency. Okay. Because you have to evaluate the objective function, which costs computational. For example, from our region of interest from S to AF. Okay. We, for example, we evaluate 8 points. Okay. That means we divide the region of interest into 9 regions. Okay. And then you see that we can eliminate 7 out of 9, right? Okay. So we have to keep at least 2 regions. Okay. So in one step, you see that we can reduce the area of interest from n+1 to 2, right? Okay. Where n is the number of points we evaluate. Okay. For example, this one. And we have dichotomous search. Okay. For dichotomous search, you start from the midpoint, and then from the midpoint, we move to the left by delta, half of the delta. Okay. And you can move to the right, half of delta. Okay. It depends on the size of delta. Okay. But with this dichotomous search, you assume that, well, the local optimum is likely in the middle. Okay. Okay. So what else? Interval halving. For interval halving, we in the very first iteration, we start from midpoint, okay? And quarter, okay? Of course, third quarter, you need 3 points of evaluation in the first run, okay? And you can reduce the size of the area by half. There's a reason why we call interval halving, okay? Because at each iteration, we can reduce the area by 50% always, okay? For the first one, of course, you have to evaluate 3 points, okay? But for the next iteration, you need only 2, okay? Why? Because you see that we evaluate x1, x0, and x2, right? Once we remove the right hand side part, you see that you don't have to evaluate x1 again because we already obtained it, right? You need only 2 points. It's a quarter of this, also third quarter of this. Okay, from 0 to x0. Okay, and this is a summary. Okay, how the area shrink at each iteration, starting from the first iteration and then, well, the second iteration. What happened? Okay, so that is about elimination method. The next one is interpolation method. For interpolation method, it's different. For example, the first one is quadratic interpolation. For quadratic interpolation, we assume that our objective function is quadratic function, okay? The good thing about quadratic function is once we know the quadratic function, okay, we know the minimum point, right? Minimum point always at minus b over 2c, right? So if your objective function is exact quadratic function, you will get solution in one iteration, right? But if it's not, of course, you need multiple iteration, maybe. Okay. So because we don't know our objective function, right? We assume that. We assume our objective function to be the quadratic function, and we need 3 parameters, okay, in order to define the estimated quadratic function. Okay, so because you need 3 parameters, you need 3 points, right? Assume that we going to evaluate at lambda A, lambda B, and lambda C, okay? And you need objective function at lambda A, okay? We call it FA. And at lambda B, we call it FB, okay? And at lambda C, it's FC, all right? Okay, you need 3 points. Okay, and with that information, of course, you can solve the problem by yourself, right? 3 is algebraic. It's a system of equation, but anyway, you can use this formula also, yes? You see that A is a function of if A, if B, if C, right? And lambda A, lambda B, lambda C, right? B also, C also, right? So minimum point is at minus B over 2C. And this is our example. The next one is cubic interpolation. Okay. For cubic interpolation, of course, you need A, B, C, and D, right? Because you approximated a third order polynomial, okay? So actually you need 4 points, right? But even 2 points is enough. Is enough. Lambda A, lambda B is enough, but you need derivative. Okay? So if you don't want to use derivative, of course, you need 4 points. And you have to derive the formula by yourself, okay? Because this formula is related to derivative. Okay? This formula relate. You see that this formula you need derivative, right? F prime B, F prime A. Okay? Okay. And the next one is Newton method. For Newton method, actually it's the idea is, well, we approximate the objective function as a quadratic function also. Okay? But we don't explicitly derive the quadratic function like that, like we did before in quadratic interpolation. This one, we use Taylor series, okay, to expand the objective function at lambda I. Lambda I is our fixed point, okay? And we expand it to using linear term and quadratic term, okay? So you see it's actually the quadratic function, right? And because we want the minimum point, right? The minimum point, we can find the minimum point by just take derivative of this function respect to lambda, okay? So we get this formula, this expression, okay? And this is the condition for minimum point. The derivative must be 0, okay? So you rearrange this expression again to obtain lambda I, okay? And you get lambda I plus 1, it's lambda I minus f prime lambda I over f double prime lambda I, okay? Okay? And because this one, for Newton method, you need information of f prime and f double prime, okay? And you need analytical method, right? To find derivative and second order derivative. And if we replace this f prime derivative and second order derivative by using numerical method, we call it quasi-Newton method, okay? Okay, so it's done here. So screen, okay, all right. Now we can look at our Jupyter notebook. You can open the, well, it's using Colab. So I have updated, okay? the file. So in the file, of course, I include some explanation, short explanation, and also the step-by-step process. You get the file? You download it again in my course view or online through Line. It's okay. In the previous version, of course, I omit the step-by-step process and some short explanation here. Okay. And also I adjust the code. Elimination, of course. Open elimination first, not interpolation. We're talking about elimination method first. So here I show you the exhaustive search, dichotomous search, and interval halving. Okay. For the first one, exhaustive search, you define the objective function here. Okay. In this code, objective function. The objective function in this file is cubic x, right? Plus x minus 2 square of x minus 2 and plus 1. Okay. And we use exhaustive search, which we require function. Okay. We're going to, of course, this is only the model of it, model of the function. Okay. So this function takes parameters on the objective function we define. Okay. And also interval and number points. Okay. If you don't define number points, it will take 100 as default. Okay. 100 points. Okay. So the code for exhaustive search, it's here. Okay. What I highlighted here. Okay. So we take here xmin, fmin, and iteration result. Okay. By calling the exhaustive search function, this function is, which is defined here, right? Already defined here. Okay. And this one, we take the objective function. Okay. And this objective function, I already defined here. Okay. And what else? We take interval. Okay. So you have to define the interval and the number of points. Okay. But you don't have to define it, because if you don't define, it will take 100 as default. 100 points. Okay. But of course, if you want to specify the point, like 50 is all right. Okay. If you override this 100. Okay. So we run it. Yes. I run on my computer, not Colab. Sorry. Yeah. But you can use Colab. Okay. So okay, so this is the result obtained from each iteration. We start from 0, right? X1, X2, X1, Fx2, okay? It's ranging from -1 to 4 as specified here. Where is it? Yes, this here. I start from -1 to 4. Okay? And you see the the area of interest shrinking down, okay, from -1 to 4, it shrinks to -1 to 1.5, okay? And once we run it again, it shrinks to 0.24, okay, to 1.5, and again, okay? So the area of interest shrinking down. Any questions? Hmm? Okay. But what you want to see? What? Pardon, say again. Really? You download it from my course view? I see. Because when you download it from my course view, you have to change. No, the what is it? It's the type of the file. Because if you add automatically .txt, it's text file, right? You have to remove that extension. Now, once you download it, yes, it becomes a text file, right? You use computer? Anyone use computer? No one? It's okay, but what I want to tell you, it's actually Jupyter Notebook. It's a text file actually, but it's interpret different way. So if you download it from my Courseville, the Jupyter Notebook, the extension of it, it's IYP something. Let me check. Dot I yes IPYNB, right? Yes, but my Courseville at .txt as an extension after that IPYNB, right? So once you download it, you have to remove that .txt extension out, okay? We need extension of .ipynb. No, it's .ipynb.txt. Right, so you have to remove that .txt out, okay? Or it's okay. Yeah, I can upload to Colab and then you can use from Colab. Just one moment. You know how to use Colab, right? Colab.research.google.com. Okay. And well, I'm uploaded. Just one moment. Elimination method. Okay, good. Okay, then I share it. It's not restrict. Yes. Copy link. Done. Okay. I paste the link of Colab in the Line group already, in our Line group. So you can open it that from that Colab. Can you open the Colab? Okay. Okay, good. So you can run it, right? Try to run it from Colab. I'm confusing because I have two copies of it. One is running on my computer and the other one run on Colab. Which one is it? Okay, so this one should be Colab. Okay, good. Yes, this is Colab. Hmm? What? Hmm? Why it's 50? One moment. Okay, sorry. Remove that comma 50 out at this line. Because we have to specify endpoints equal something. Okay. If you don't want 100, of course you have to specify that endpoints equal 50. Oop. What? What? Yes, this is the correct way. Okay. Okay. But of course you can remove this part. Okay. If you don't want to specify, because we specify the default here. Okay. Okay. So you see how it changed. This is the result from the first run. Okay. We divide to 50 interval. Okay, from -1 to 4. Okay. Then we find the minimum, right? The minimum points. And then you take 2. Okay, and can around the minimum point. Right? Let me see your screen. I want to know how it looks on iPad. Okay. You can run it even on iPad, right? Yes. Okay, good. So maybe from now on we use Colab. It's easier for setup. Also, if you have problem with Python, I recommend that you can find some tutorial on Python on YouTube. We need only basic of it. Okay. Pardon? Python? No. Only to improve your understanding on how each algorithm works. Yes. Yes, you can use MATLAB, but I don't have enough time to prepare material in every platform. Previously, I used MATLAB, of course, yeah, but
You see, in brain background for the computational calculations, MATLAB is more widely used.
expensive. All right, so the only one thing it's expensive, and once even you graduate already, now I know you have license because university pay for the license, right? But once you graduate, cannot cannot guarantee whether you can access to MATLAB. Okay. But here, if you are familiar with Python, it's the tool is quite good, and you can access it for free. Okay, so now we move to dichotomous search. Okay, for dichotomous search, again, in this file, I add short explanation and step-by-step process. Okay, and you see that we evaluate the midpoint point, right? Let's say we start from A and B, okay? So we look at the midpoint, which is, this is what's it, midpoint, okay? And then from the midpoint, we move to the left by delta, half of delta. We move to the right by half of delta, okay? And then we evaluate fx1 and fx2, okay? Then narrow down the interval by comparing x1 and x2, okay? So in this code, okay, starting from here, you can play with objective function, okay? You can change to your own objective function. And then what else? This is the function to perform the dichotomous search, okay, here. We specify an epsilon and delta, okay? What is epsilon here? Epsilon is tolerance, okay? And delta, it's what is it? The delta is delta, right? Actually, we should, yeah, let us check it first, run it first. If it's have any problem, we can solve it. Okay, good, no problem. Good to see that. Okay, so so once we, yes, this is the code to perform the dichotomous search. And the next one here, we call this function, okay? We specify objective function and interval, okay? We omit epsilon and delta. We use the default, okay? But of course, you can specify by yourself if you want. And the result show that, what is it? Starting from, yes, -1 to 4, which is the original or initial range, right? From -1 to 4. And it shrink down to -1, -1 to 1.5 and keep shrinking. Okay, so at 15 iteration, this is our region of interest from 0.8684 to 0.8685. Okay. And of course, if you need higher resolution, you can perform more, right? You can change epsilon. And I plot all of these, yes, in the graph. Okay, any questions? Any questions? Yes. Please make sure that you understand the algorithm. You can calculate it by yourself. I may ask you to calculate 1 or 2 iteration. Okay, by using specify delta or specify, yeah, objective function and range, thing like that. For 1 or 2 iteration, I'm quite sure that you can do by using calculator. The next one is interval halving. Okay, it is fine. I put some explanation and step-by-step process again. First, we define the objective function and select the search interval cross from A to B and termination criteria, right? Termination criteria, epsilon. What else? Yes, we calculate midpoint and quarter, third quarter, okay? Okay, then we repeat the algorithm until it's converged. Yes, okay, good. So the algorithm start here, okay? Interval halving track and return this x-min function, the value of the objective function at x-min and also iteration because I'm keep tracking it. Okay, and here we call that interval halving. Okay, specifying the interval from -1 to 4. Okay, actually the function accept 3 arguments. Okay, the first one is the objective function. The second one is interval, right? And the last one is epsilon. Okay, we specify epsilon already. Okay, yeah. Okay, so you see the midpoint change, okay? And it converges to the same point, I think, 0.868, yes. Should be the same point, yes. 0.868, right? Yeah. It's algorithm, luckily, all algorithm converge to the same point. Okay. Okay, any question? No? No question? Okay, then we move to interpolation method, right? But before we move to interpolation method, if you use Colab, you see here, right? RAM this, yes, you disconnect it first. Disconnect and delete runtime. Yes. Yes. Why? Because if you don't disconnect it, it will not allow you to run more session. Okay, because you run the what's it, free credit. Okay, it allow you to run 1 or 2 sessions at a time. Okay, so you disconnected it first. Okay, then I will upload the new notebook. Interpolation method here. Oh, I turn off microphone. Oh, no. I understand now. All right. It's microphone on this notebook. Yes. I thought that I turn off, I mute my microphone and no one remind me about that, but it's all right. Yeah. Any questions? Oh, yeah. Speak slowly. You mean in practice, right? It depends. You can see. But in exam, no. You have to because in exam, you have to do which part of it is. Yeah. Exam, you have to do it by yes. 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 I think, of course, the initial range, you are given with initial range. Yeah. It's the range is from 0 to 5, right? Yeah, this is smaller than this one. You can plot it. You see that 0. You give me the value of that. You have 0, 1, 1, and you give me the coordinate. At 0, it's 0, right? Yeah. 0, 0, right? X is 0, Y is 0. F. Yeah, now it's 5. X is 5. 0, 5. Okay. At 0, you get 5. At 0, you get 5. 5. Okay. And the next one. What is the 5? Right? We start from 0 to 5. What is the value at 5? Minus 25. 147. Huh? 147. Minus 25. Okay. And what's the midpoint? Five is 1,000 something. 1,000 something. Right? Yeah, it's minus 2.5. It's 25. Minus 25. Minus 25. Point something. Point what? 146. 46. Okay. What is the value here? 2.4. I know. Yeah. The value of that. Minus 25.47. Minus 25.47. Just that? Okay. We see. What about here? Minus 25.46. Minus 25.46. Okay. Which one is larger? This one and this one.
This one is 4687 into the center. Yeah, this one is which one is larger? This one is larger. No, this one is this one. The other one is larger. Here it's the lowest one. And what about this? And this, which one is larger? This one is larger. Okay, let's say this one. Okay, and here, all right. This is correct. Even it's smallest, of course. This is not too scale. Okay. So where is the minimum point? Should be around here. Okay, you keep this area. And it's done.
Okay, so I will share you with copy link and then done. Okay, you got the link, right? You can open it. Okay, good. If you run it, the first run, it will automatically connect. But it will not automatically disconnect. Okay. So for quadratic, this is the first example because in this file, we deal with quadratic interpolation and quasi-Newton method. Okay. I skip the Newton method because for Newton method, you need to specify the gradient by yourself, right? Derivative by yourself. But here we use quasi-Newton method because the gradient information is calculated by numerical. Okay, this the first one. Yes. It is. Yes. It's running, right? Let me see. Okay, it's updating. Okay, good. Good to see that it's converged to the same point. X minimum, do you remember from the previous one? Our minimum point is somewhere around 0.8685 around here. Okay. And here, using quadratic interpolation, we got the same result. Okay. And you see from the algorithm, what do we need? We need x0, x1, and x2. Okay. Here, x0, x1, x2. As we previously discussed, we need 3 points, right? For interpolation, quadratic interpolation. Okay. And when you run it, where is it? Yes, you specify the objective function here. Okay, you can move to the upper part, but it's all right. And yeah, here you specify the objective function. You specify the first point, second point, and the third point. Okay. Yeah. This is x min, and then from around x min, we take x min to be our x1. Okay. We from the first iteration where well the algorithm take 1, 3, 5, right? Okay, 3 points, and it's calculate the x min at 1.35. Okay, then we know that from the first run the minimum point is around that point. Okay, 1.35. Then we take that as our x midden point, x1 point. Okay. Okay. And then well, we're shrinking down the region. Okay. Keep closer. Keep all 3 points closer to the minimum point. Okay. We eliminate the what's it? This point is 5 to 5 because it's far away. Yeah. Okay. And the second run, second iteration, you got 0.9764. Okay. And this is will be our new candidate. Okay. So we take this as our x1 point. Okay. And the previous x1 becomes x3. Okay. Any questions from Zoom? No? Okay. And the next algorithm is quasi-Newton method. Okay. For quasi-Newton method, we compute the Hessian. What is the Hessian? Hessian is second order, right? Yeah, normally it's second order. Okay. Second order derivative. Okay. Wow, it's what's written here. It's wow. It's for multi-dimensional. Okay, but our focus is single variable. But you can apply anything anyway. You can look at the code. Our code takes only one variable. And what do we need here? Yeah, numerical gradient. How we calculate the gradient. And the next one is second order. Okay, second derivative. Okay. And this is the code for quasi-Newton. Okay. Stop here. Well, yes. No. Stop here. Sorry. Return. Okay. Return x, function of x. Okay. Then this is the objective function. Okay. And then we run here. Quasi-Newton. Okay. we keep tracking the minimum point obtained at each iteration. Okay, we should run it first. Okay, so luckily we obtained the same result. Okay, x is 0.8688. It's about the same. It depends on epsilon. Okay, if you need higher precision, of course, you need to adjust the epsilon. Okay, but this one take only 4 iterations. Okay, so from what is it? Quadratic interpolation and quasi-Newton method. If your objective function is a second order, no, not second order, quadratic function, you will get the solution in one iteration, right? If it exact quadratic function, okay. If not, of course, well, you need multiple iterations. Okay, so let us break for 10 minutes, okay, and then we come back and continue to, yeah, the what's it, direction, how can we find the direction. Okay, so ready? Well, now let me tell you again the importance of unconstrained optimization. You see that what we learned from the last week. Wow, it's only applying for unconstrained, right? Unconstrained because we haven't considered the constraint yet. Okay. The algorithm we developed that it's well, we find the direction and then we find the step size, right? And then testing it. We never consider the constraint. Okay. We will deal with constraint later. Okay. Even this week, we will not consider the constraint. Okay. But why the unconstrained optimization important? Because, well, in some case, even in practice, I mean, in real world problem, you have constraint. However, if the constraint, those constraints are away from your optimum region, I mean, the region of your interest, then you don't have to consider the constraint, okay? Because it's too far from the local minimum point or maximum point, depends. And also, if you have to consider the constraint and you need algorithm to deal with it, deal with the constraints. Most of the algorithm, well, designed for handling the constraint, you still need unconstrained optimization problem. Why? Because those algorithms just convert the constraint optimization problem to unconstrained optimization problem. Okay. Then you need unconstrained optimization anyway. Okay. And also the study of unconstrained minimization techniques provides the basic understanding, okay, for the real problem. Okay, so that is the reason why you need unconstrained optimization. And previously, the condition that define the minimum point is, yeah, the stationary point, right? The stationary condition, like in KKT, no, sorry, necessary condition, not KKT, because in KKT, we already consider the constraint, okay? The derivative of the objective respect to each decision variable must be 0, right? Do you remember that? Okay. Okay, so previously we discussed about the whole algorithm. We find the direction and then we find the step size. Okay. In the first step, we convert n-dimensional problems to one variable, single variable problem. Okay. Multi-variable problem to single variable problem. Okay. So no matter in the original problem, you have multiple decision variables, but once you define the direction, it becomes one variable, which is step size, right? Okay, so we learned about how to define the step size already, okay, previously. So we omit the first part, how to find the direction, okay? And we can broadly classify the algorithm to find the direction based on two different techniques. The first one is direct search method. And the second one is descent method. The first one, direct search method. We rely on information of the objective function itself, the value of the objective function, not the derivative, okay? We have random search, grid search, univariate method, pattern search method, like Powell methods, okay? We are going to explain it. And the other class is descent method. For descent method, you need gradient information, derivative information, okay? For example, steepest descent, Fletcher-Reeve, Newton method, and Marquardt method, or quasi-Newton method, okay? All of these algorithm need derivative information, okay? But on the left hand side, this algorithm do not need derivative. Okay, it's relying on only the value of the objective function. Okay. Okay. Any questions? No. Okay. So for the whole algorithm, it's the same. We define the direction, right? Direction is S, right? And lambda star. Once we define the S, we find the lambda star. Okay. Okay. So, and also we define the rate of convergence, how to stop the algorithm by checking the rate of convergence, or, well, several method. Here you can read it later. Okay. I'm going to start from the first one, the algorithm itself. The first one is random jumping method. Random jumping method is kind of a direct search method. Okay, it's kind of random search based on the use of random number in finding the minimum point. So if you work on what is it, the n-dimensional, okay, so each vector, okay, you random it, just random it. You get an idea? Just random it. Which direction is? No, we don't know. We rely on random, just random. Okay? And if you random the direction, then of course, if that direction is not correct, don't worry, just random. Keep random it until you get the direction that leads you to what's it? The new point which smaller objective function. Okay? So in this case, it's if xi is rely on li and ui, right? You random it, the number between lower bound and upper bound, just that. Okay, sometimes we call it random walk. Okay, so the algorithm starts from initial point, right? And then you find the objective function, you set the iteration, and you generate a set of n random number. Okay, it depends on the dimension of your problem. Okay, and from this generated vector direction, you convert it to unit vector. Okay, because no matter you transform it to unit vector, it's represent the same direction. Okay. Okay. You work on the random number itself, R1 to Rn, or you convert it to unit vector. You use the same direction. Okay. And then compute the new vector corresponding to the function value. Okay. This lambda, you find the lambda based on that direction. Okay. Find the minimum point. If you get smaller value, then you accept it. Okay. And you get new point. Okay. And very easy, you see, but not efficient because maybe you run for, well, the computer takes effort, excessive effort in order to solve the problem. Okay. Because you haven't given any guideline for the algorithm. Okay. It's just random. Okay. Shall we start for a while, look at the code? I think it's good to, or should I explain everything first? We can look at the code. Okay. Okay, for now, let me share it first. Okay, we start from random. Okay. Actually, it's not efficient at all. Okay. Here we have two variables, x0 and x1. Okay. And it relies on the random. Okay. And then we find the best candidate. Okay. And this is how the solution evolve. Okay. But sorry that it's we cannot obtain the optimum solution in this code. Okay. We start from here and it's lead to outside this region. Okay. Let me check again. The next one is random jumping method. Okay. Random jumping is I already explained it. Just one moment. Okay, the same class, random jumping and yeah, random walk. We should move to the next one. Is a grid search. For grid search, this one it's quite was it is more efficient than random, but it's requiring heavy computational efforts. Why? Because imagine that you have two variables and you want to evaluate all the region here. You divide the first parameter, for example, first variable to a number of grid, and also the second variable, you divide it to a number of grid. Then, for example, you divide the first decision variable to 3 regions, and also for the second variable, for x2, you divide into 3 regions. So you have 9 regions to explore, right? Okay. So if your space, search space is too large, this become excessive. Okay. Computational time becomes excessive because it's spent too much time to explore. Okay. But this is also one of the algorithm we can use. Okay. In some case, if we're dealing with the global optimization, where you don't know, you cannot guarantee the whole space as a convex for the convexity, or you know that it's a global optimization problem, then you have to evaluate every point, right? Then you can use grid search method, okay, as was it a starting algorithm to generate initial point, okay. But in this case, we don't rely on other algorithm. We just use grid search method only. Okay. Then once you define each grid, okay, each space, small space, then you take the centroid of it and then evaluate the objective function. Okay. Which one is smaller, then you take that one. Okay. Okay. We also have code for that. Where's grid search? This is random jumping, just random walk. Indirect exploitation. Yeah. Okay, this is grid search. Okay, this is how it look like. You divide your space to multiple grid. Okay. For example, in this case, we divide our grid to how many? Just one moment. Grid size is 50. We divide each variable to 50 region. Okay. And then we evaluate each region. Okay. So it's not efficient at all. But this is one technique to get the problem to get the result. Okay. Now we move to other technique, which is sound more interesting. It's univariate method. For univariate method, well, we start from the direction. What was it? Just one moment. If we work on n dimension, you take one at a time, okay? And the rest becomes zero. What does it mean? It means that the first direction we take, we consider, is the direction follow the first variable x, okay? For example, if you have x and y, right? This one, x is 1, y is 0. What does it mean? You follow the x direction, right? Okay. And the next step is you change the direction to 0, 1. Okay. If you have only two directions, then the next step, you come back to x direction again and solve the problem. Okay. And y direction and x direction, zigzag. Okay, so now look at the code. For example, if our objective function contains two variables, x1 and x2, okay? This is our objective function. We take the direction of x1, it's, no. This is initial point, not direction. x1 is 0, 0, okay? This is our initial point, okay? And our first direction is 1, 0. Okay, so you have direction of 1, 0. There are two ways to go, right? To the positive or the negative. So we have to evaluate whether if we follow the positive side or follow the negative side, we obtain increasing or decreasing of the objective function. Okay. So, for example, in this case, we want to minimize f, and we test on this direction, this 1, 0 direction. If we take the positive side, we obtain the objective function as 0.0102. And if we take negative side, we take minus 0.0098. Which way to go? We should take positive or negative? Pardon? Negative? Yes, we should take negative, right? Because we want to minimize it, okay? Then the direction, the correct direction, it should be minus 1, 0. Okay? So once we apply this direction, minus 1, 0 to our line search pattern, the new x equal initial x, x1 plus lambda s1 star. And s1 star is minus 1, 0, right? So we can write the objective function as a function of the step size, the lambda, okay? So f becomes minus lambda plus 2 lambda square, this one, right? You get an idea? And this is the reason I told you earlier that our whole algorithm, we transform the objective function, the original objective function, which is a function of multiple decision variable, to the objective function as a function of one variable. You see, this we have only one variable here, right? We have only lambda. Okay? And then you know how to solve this problem, right? We have f is minus lambda plus 2 lambda square. You can use elimination method to find lambda or interpolation method to find lambda star, right? Okay? But by analytical, you see that this is quadratic function. You get the solution, exact solution for sure. Okay? By using maybe analytical solution of it, because it is already quadratic function. Any questions? Yes or no? Okay, then from the first step, we take the direction of 1, 0. We obtain the solution at lambda quarter, okay? So we substitute back here. So the new point is minus quarter 0, right? This one, minus quarter 0. Okay, this one. You see my cursor, right? Okay, minus quarter and 0. So then what does it mean? By one iteration, the solution evolve from 0, 0 to quarter 0. Okay? You get new solution. And then from this solution, we take the next direction. This time, we follow 0, 1. As I mentioned to you, that we follow a zigzag. First, we follow x direction, then we follow y direction. Okay? We take 0, 1 direction. Okay? So here we evaluate the objective function at this point first, and then we find which direction we should go. Of course, we consider 0, 1, but we don't know we should go positive or negative. Then we use the same, okay? We take small value of lambda first, okay? And with this direction to positive and to negative, and then we evaluate the objective function, okay? If we take positive, we obtain minus 0.1399, okay? If we take negative, we obtain minus 0.1099. Which way we should go? Positive or negative? Yes, positive, right? So the correct direction should be 0, 1. Okay. Then we apply this direction 0, 1. So we write x3 as a function of lambda. Okay. x3 is x2 plus lambda s2 star. We know s2 star already. S2 star is positive 0, 1, right? Okay. And what is xt? X2. X2 is minus quarter and 0. Okay. Then we write the objective function as a function of lambda. Okay. Luckily, it's a quadratic function again. So we solve for lambda. Okay. Lambda is 0.75. Okay. Once you obtain the step size lambda, you substitute it back to obtain x3. Back here to obtain x3. Okay. Now we arrive at minus quarter and third quarter. Okay. The solution evolved from minus quarter 0 to minus quarter third quarter. Okay. Then we go back to x direction again, 1, 0, and we repeat the algorithm. Okay. We find which way to go. Okay. Positive or negative based on this vector 0, 1. Okay. And find lambda. And you substitute it back. Okay. Okay. Any questions for this algorithm? Univariate algorithm. Why it called univariate? Because we follow one direction. I mean, direction follow the direction of the axis of the each variable at a time. How do we know optimum point? You repeat it until the conversion rates close to 0. Okay. Once you reach the point that even you change the direction from x direction and y direction, you obtain the same solution. No reason to repeat it, right? Or you obtain the solution which is already satisfied the stationary point. You don't have to go further. Okay. So the good thing is you don't need derivative to find the direction, because always you keep the direction on x and y, right? If you have x1, x2, x3, you keep direction of x1, x2, x3, and then follow x1, x2, x3 like that. You don't need information of derivative at all. Okay, but it is quite robust because you don't need derivative. But the problem is it takes too much time. Okay. It's better than random search, of course, because at least we follow some guideline. Okay, so let me show you the code. This is the univariate method. And Okay, you can look at the code by yourself again. At least it's obtained solution, but I haven't checked it thoroughly. Mm-hmm. Yes, you see here, it's a, we test whether we move to the negative side or positive direction or negative direction, okay? And this is our initial guess. Okay, now we move to the next algorithm. Previously, we learned the very simplest algorithm where we follow each direction at a time, 1, 0, 0, or 0, 1, 0, and so on. The next one is pattern search direction. The algorithm, they still the same. We replace with the direction here. You see, in the univariate method, we search for the minimum along the direction parallel to the axis, right? The direction belongs parallel to x1, and then the direction parallel to x2, and then we back to x1 again, x2, x1, x2. You see, right? And you see, if we plot, if we keep record about the change, the how the solution evolve, you see that we have one direction and the second direction here. Okay, you see that we have two directions, right? The first one, it's a odd number. When for the first iteration and third iteration, fifth iteration, and the other direction is from second and fourth. Okay, and once you see that, once we use univariate direction for 4 steps, we obtain this pattern, right? Okay, so then we have guidelines, some guideline. You see that the evolve of solution follow this direction and this direction. Then once we obtain this point and this point, of course, from the beginning we obtain it, then you take vector of this and apply in the next step. Okay, you get this vector. And then you can use this direction in the fifth step. Okay. What about the sixth step? The sixth step, you can sixth iteration. We can take the vector from the second iteration to fourth iteration. Okay, we take this vector and apply it in the sixth iteration. Okay, and again, for repeating this, we can apply the new direction we obtain from the vector from third iteration and fifth iteration. Okay. Okay, you get the point. And this one, this method, we call it Powell's method. Okay. And then you see that we have two directions. this direction, right? And this direction for odd number and odd number iteration and even number iteration, right? So sometimes we call it conjugate direction because we have two direction, which is conjugate. Okay, so we can take this. Okay, from let me stop this first. And yes. Okay, so for Powell method, we consider this objective function and the same starting point 0, 0. Okay, the first one we know they at this point the objective function is 0. Okay, and then we take the univariate method first. Okay, and find the lambda. Okay, and we repeat it from univariate method, and then you see that from the fifth iteration, I think this is still second S2. Sorry, yeah, this is S1, right? It's univariate. We take direction of 1, 0, right? And the second one, we take direction of 0, 1, okay? Which is univariate method, right? Then what about S3? Where is it? S3. Okay. This one is P1. We take direction of x4 minus x2, which is a vector between x2 to x4. Okay. You see that from the fourth. No, not from the fourth. From the fifth, our direction changed. Okay, because from the first four iterations, we don't have any information, right? We have to follow univariate method first, and then once we have all information in order to construct that vector, as I show in here, right? From this step, you need univariate. This step also univariate. This step also univariate. Okay? But once you obtain it, this point, the next one, this one, you can apply this direction. Okay? And the next point, you can apply this direction. Okay? And you see here. Okay? Okay, we have Powell method here. Oh, sorry, I'm so lazy because I called was it the library? Okay, I have time. I will replace it. Because we don't calculate by ourselves, we use the library. Here you see the minimize function with this initial point and use method, Powell method. Okay. If you want to know how the algorithm works, you have to check this library. Okay. Okay, but it's okay. from 1, 1. Okay, we approach 0, 0. Okay, why is univariate method? It's not univariate method here. Oh, sorry, I should run this Powell method. Okay, here's Powell method. Okay, 3 iteration, we obtain the objective function of -519. Okay. Okay, so back to okay. Any questions regarding Powell method? You know how to find the direction, right? At each step. Okay, the next one is simplex method. For simplex methods, the direction, you find the direction from the, what's it, centroid, the vector from the words point, the point having the words value of the objective function. Okay, the vector from that point, the words point to centroid. For example, if you start from 3 points, okay, the algorithm requires 3 points. Let's say x1, x2, and x3, okay, and you find the centroid. You know that if x3 is the worst point, you should not go that way, right? You should not go the direction leading to x3, right? Because x3 is the worst point. Okay? And which direction do we need? We have to go away from x3 because x3 is the worst, right? So we should follow the direction, the vector from x3 to centroid. Okay? We find the centroid of this 3 point first and then, well, follow the vector from x3 to x0. x0 is the centroid of it. Okay, so we start from centroid. How to calculate the centroid? Centroid is calculated by summation of xi and divided by n. Okay. In this case, n is 3, right? Okay. And then the vector, that vector, it's, well, the vector from xh, which is the point with highest value of the objective function, to the centroid. Okay. And how far we should go? We should take, well, alpha. Okay. Where alpha is the ratio of distance between xr and x0 and h and 0, x0. Okay. What does it mean? It reflects that, well, you're going to project the value from the words point x to through the centroid to the other side, to the opposite side. Okay. And then we have modified algorithm of it. It's a XE, which is define how far we should go from that vector. Okay. And this simplex method, you don't have to solve the problem of the finding the step size separately because it integrates into the same algorithm here. Okay, let us look at the example. Consider these 3 points. We start from these 3 points. X1 is 4, 4. X2 is 5, 4. X3 is 4, 5. Okay. Then we take alpha of 1, beta of 0.5, and gamma of 2, okay? At x1 first, we evaluate the objective function here. And the objective function is 80, okay? Is 80. At x2, the objective function is 107. And x3, we got 96, okay? These 3 points. Which one is the best? Which one is the best? X1, right? We minimize it. What is the worst? F2, right? So we call this one, the best one, as XL, okay, lowest. And this one is XH, okay, the highest. So we should go away, move away from XH, right? But we will project it through centroid, okay? So we have to find the centroid first. In order to find the centroid, we don't take XH, okay? We take XL and the other one, okay? We take X1 and X3, okay? And find the centroid. Because we take only 2 points, then we have to divide it by 2, okay? If you work with not 3 points, 4 points, 5 points, for example, if you work with 5 points at the beginning, you have 1 point, which is H, right? You still have 4 points. Then you take centroid of these 4 points, okay? But here we work with triangular, okay? 3 points. Then we take only 2 points. Okay, so our centroid is 4.5. Okay, and the objective function of the centroid is this value, okay, 87.75. Okay, so we will project from x1 through centroid. Okay, so you see, not XL. We will project from x2, which is the having highest objective function, through the centroid. Okay, we take XH and centroid. So our XR trial vector is calculated from centroid and XH. And why we take 2 here? You check the formula again. Our formula is 1 plus alpha x0 minus alpha, okay? And if our alpha is 1, you see that we have 2 here, right? And minus 1 here. Okay, 2 here and minus 1 here, okay? Then you calculate it. The XR is 3.5, okay? With alpha is 2, we get new point XR at this point. Okay, the objective function of XR is 71. Okay, and then we have to consider if FR is better than FL or not. What is our FL? FL is 80, right? XR is better, right? We should extend, well, to the new point, XE. And XE is calculated by gamma of XR plus 1 minus gamma of X0, X centroid. What does it mean? We project, the first one, we project from XH, right, through centroid. And the next one, we know that in that direction, we obtain better solution, even better than the best one in the previous round. So we should go further with that direction and obtain XE, okay, extended. Extension of it, okay. Okay, so we obtain new point XE at 5.5, okay. And the objective function of this point is 56. Okay. Then we replace XH with XE because we obtained XE already. Okay. We replace the worst in the previous round with the best we obtained. Okay. So in the next round, we have X1, X2, X3. Okay. We replace XH in the previous round. Okay. What is the XH in previous of? 5, 4. Okay. You see, we replace that 5, 4 here. Okay. So now the best one is this one. X2 is our best point. Okay. And F3 here is the XH in this round. So we're going to discuss this one for sure in the next round. But first, we find the centroid. And we project from centroid through, no, from XH through centroid. Okay, we obtain this point, X0. Okay. And F0 is here. Okay, 67. Okay. And this is XR. We calculate XR. Okay, using the same alpha. Okay. You obtain new point XR and FR, which is even better than the best one in the previous round. Okay. So you further calculate XE. Okay. XE is even better. So you replace XE obtained here. Okay. Replace the XH by this one. Okay. Now we arrive new set of 3 points. X1 objective function is 80. This one is 56.75. And the best one we just obtained is 25 point something. Yeah. Okay. This is the burst XH. This is XL. No, this is not XL. XL is here. Sorry. Okay. So you find centroid. Okay. So sorry, this one I should write XL. Okay. Okay. You repeat the algorithm. Okay. Then you repeat the algorithm until all 3 points comes, well, approach the same point. Then you can stop. Any questions? No? Okay, so We look at the code. Hopefully, I don't use the library. This is simplex method. Okay. Yes, I use library. the, the other name of that simplex method, we call it Nelder meet. Okay. And yes. And this is how it evolved, starting from here and move to this point. Okay, so now you know about simplex method. We move to the next one. The next algorithm is steeped descent. For steeped descent, is totally, at the beginning, I told you that we have two classes of algorithm, right? The first class is direct search method. And the second one is descent method. The first one, we don't need derivative, right? Even univariate method and power method, it doesn't. They don't take information of derivative, right? Now we move to the descent method. And of course, we need derivative. Okay, what is the steepest descent? When I say, wow, steepest descent direction, what does it mean? It's the steepest, right? So for steepest descent, you take minus derivative, okay? This is the direction that we approach the minimum point. Wow, this is the fastest way, right? If the shortest path, the shortest direction to approach the minimum point. You take the derivative, which is a low, okay? And then you take, what is it? Why we take minus one? Which it is a direction perpendicular to, is on, or it's autonomous of the slope, right? Okay. And then once you get the direction, we use the same formula, okay, in order to find lambda star. Okay. And for lambda star, of course, you have many algorithms. You can use elimination method or interpolation method, whatever you want. Okay. For example, we take the same example. Okay. We start from the same point, 0, 0. We find the derivative. And of course, the direction is minus of derivative. So the derivative at this point is 1 minus 1. So you take the direction of minus 1, 1. Okay. And then you substitute. We rearrange the equation again. Our objective function now a function of lambda. Okay. Single variable. And then you find the minimum lambda, right? The lambda which leads to minimum point of the objective function. So the new point is minus 1, 1, okay? From minus 1, 1, you find new direction, okay? And from this direction, you find S again, okay? Repeat it until you obtain, until the solution converge. Okay, any questions? Okay, so we look at the code. I'm quite sure that I use library again. Oh no, yeah, I write by myself. There's several version of it, of this code, of the code. Okay, this one we take the derivative. Where is the derivative? Yes, we calculate that gradient. Yes. Huh? Is it recording here? What does it mean? Is it recording now? Okay. Okay. So we find the gradient using numerical method here, numerical gradient. Okay. Yes, this seabed descent and take numerical gradient. Okay. Okay. So the next one, the next algorithm is conjugate gradient. Well, for conjugate gradient, sometimes people call it Fletcher-Reeve method. Okay, the Fletcher-Reeve method, and the direction update every time. So you start from the seabed descent first at the beginning, and after that, the next iteration it use the direction from the previous one. No, the gradient at that iteration, okay, and update it with the direction from the previous one. Okay, you see that we take gradient here, right? Gradient at I iteration, and also we update it with the direction from the previous one and the information of the gradient from the previous one also. Okay, here this is important point. We call it Fletcher-Reeve. And the other thing, I mean, well, the algorithm to find the lambda, to find the step size, well, you can use anything. Okay. Most of the time we use Newton method. Okay. Okay, so you can see this example. We start from steepest descent. Okay, we take derivative and find the steepest descent direction. Okay, and then we find in the next iteration, we take information that, okay, and update with the previous one, modify with the previous direction. Okay. Okay, so this is done for today. Well, any questions? If not, you need, I'm going to give you a homework from the previous lesson, of course. Remember that our homework consists of, totally it's contribute 30, right? 30 marks. And you have finished one already, okay? The second one is here. Okay. It's a homework on linear programming. You formulate a linear programming problem and then you solve the problem, okay? So it's combined between problem formulation and linear programming, okay? You have plenty of time to finish it, okay? No rush, okay? And the next one is convex programming. You solve this problem using KKT, all right? Okay? This one also, but this one is non-convex programming, okay? Again, you use KKT, no problem. Okay. I will give this file to Mike Cosville, okay, and create the assignment so you can do it. Maybe in 2 weeks is okay. Okay. Or if you want this file now, I can send to the Line group first. Okay. Okay. Okay, any problem? Any questions? You have any questions? Okay, if not, we finish today. Okay. Okay. So have a good day.